So have you ever stopped to wonder what actually keeps your money safe when you transfer it online? Or how a booking site knows for sure that a flight seat is really yours? Well, today we're going to pull back the curtain on the four principles that make the databases powering our world so incredibly reliable.
Okay, picture this. You're sending some money to a friend. You hit send, the money leaves your account, and then your internet dies or the power goes out. Is that money just gone, floating around in the digital ether? The way databases handle this is actually pretty amazing.
The thing that prevents that kind of chaos, the very foundation of any database you can trust, all comes down to a simple but really powerful four-letter acronym. It's kind of like the silent guardian of our digital lives.
And that acronym is ACID. Yeah, ACID. It stands for Atomicity, Consistency, Isolation, and Durability. These four properties are the absolute, non-negotiable rules that make sure every single transaction is handled safely and correctly.
So in this explainer, we're going to break down what each of these letters really means. We'll use some simple analogies and even peek at a bit of code to see how it all clicks together. So let's dive right in.
All right, first up, A is for atomicity. And honestly, the best way to think about this is as the all-or-nothing rule. What this means is that a transaction, like sending money, is treated as one single unbreakable operation. There's just no middle ground. It either works perfectly and completely, or it's as if you never even tried to do it in the first place. So let's go back to that bank transfer. Think about it. It's really two steps, right? Step one, take $100 out of your account. Step two, put that $100 into your friend's account. Atomicity says those two steps are locked together. If step two fails for any reason, maybe the account number was wrong, the system doesn't just keep your money. Nope. It instantly undoes step one, putting the money right back where it started. All or nothing. This leaves us with only two possible outcomes. If every single step goes off without a hitch, the database performs a commit. This makes the changes permanent. But if anything at all goes wrong, it performs a rollback, which is basically a giant undo button that returns the database to the exact state it was in before. And this isn't just theory. This is what it actually looks like in the code. You see that begin transaction? That's the starting line. Everything inside that block is part of the atomic deal. Then the logic checks, hey, did everything work out? If the answer is yes, commit. If no, roll back. It's really that clean. Okay, so that's atomicity. Let's move on to the C, consistency. If atomicity is the all-or-nothing rule, then consistency is the strict rule follower of the group. Consistency is a guarantee that a transaction can only take the database from one valid state to another. And a valid state is just one where all the data is following the rules. A simple rule might be an account balance can never go below zero. Consistency ensures no transaction ever breaks that rule. It's what keeps the data from becoming corrupt nonsense. A perfect analogy is booking a hotel room. The system has rules, right? The room has to be available, you can't book it for 0 nights, the checkout date has to be after the check-in date. Consistency makes sure that no transaction can ever leave the database in a weird state, like having two different people booked in the same room on the same night. And again, here's how a developer might enforce a rule like that. This little snippet of SQL code is creating a table for orders, and it adds what's called a check constraint. It simply says the quantity in any order must be greater than 0. Makes sense. You can't order -5 widgets. The database will now automatically reject any attempt to break that rule. That's consistency in action.
Next up, we have I for isolation. I like to think of this as giving each transaction its own personal bubble to work in. Because in the real world, databases are busy places. I mean, tons of transactions are happening all at the same time. Isolation is the property that ensures these simultaneous operations don't trip over each other. From the perspective of one transaction, it's as if it has the entire database all to itself.
Imagine you and a friend are both updating your social media profiles at the exact same moment. Without isolation, things could get messy. Your update might accidentally overwrite part of their update or vice versa. Isolation prevents this chaos by keeping your changes invisible to everyone else until you hit save and your transaction is fully committed.
And this is something developers can actually fine-tune. They can set different isolation levels, which is like adjusting the thickness of that personal bubble. This command you see here, read committed, is a really common setting. It basically tells a transaction, hey, just ignore any changes that other transactions are still working on, only pay attention to data that has been permanently saved. And that brings us to our final letter, D for durability. This one is the ultimate promise. You can think of it as your data being written in stone. Durability is the guarantee that once the database tells you a transaction has been committed, it is saved for good. Those changes will survive a power outage, a system crash, a server restart, you name it. That bank transfer, once committed, stays committed, period. So how does a database pull this off? Well, the main trick is using something called transaction logs. Before a change is actually written to disk, the database first writes a note in a log, like a journal, saying what it's about to do. That way, if the power goes out, it can check the journal on restart and make sure everything is correct. Commands like this one are used to manage and back up those logs, making sure data can be restored even after a disaster. So, we've walked through atomicity, consistency, isolation, and durability. But let's zoom out for a second. Why does this technical alphabet soup really matter? Well, it's all about an invisible guarantee that makes our entire digital world function. These four properties are the bedrock of trust online. They're what protect our bank accounts and make sure our flight reservations are real. But all this safety comes at a slight performance cost. That's why for something like a social media feed, where being super fast is more important than being perfectly consistent down to the millisecond, developers might use a different approach. But for any system where accuracy is absolutely non-negotiable, ACID is king. So the next time you buy a coffee with an app or book a hotel room, just remember those ACID properties working silently in the background. It makes you wonder, doesn't it? What other systems that you use every single day totally depend on this all-or-nothing, rule-following, non-interfering, and permanent guarantee? Thanks for joining this explainer.